Hello everyone, hopefully I'm audible. So for today's week, we're
Yes,
going
yes.
okay, thank you for the confirmation. So for this week, we're going to discuss about some special contrast mechanism in SEM, and then we'll be talking about electron channel contrast imaging, and after that, electron backscatter diffraction. Then we will solve the problems. So in a special contrast mechanism, uh, it means like here there are certain special class of materials are there, and whatever the structure, special structure, they can only be observed through this special kind of contrast mechanism, and we get the information about this material through intrinsic electric and magnetic field. Get information through intrinsic electric field and magnetic field. So let us first consider this electric field case. Here there are two types of contrast mechanism are there. So for type 1, they are sort of the materials which are insulating, and they are used mostly in integrated circuit where with the application of potential through electron beam, an electric field is developed, and when this electron beam interact with these materials, if there will be any variation in local surface potential, then the secondary electron from those parts will be having different energy, for which they will give image contrast because of those difference in energies, and this we sometimes also refer to as a voltage contrast. So here electron beam interacting with material, variation in local surface potential give us different imaging, for which we get different contrast. And as there is difference in surface potential, this different surface potential is giving us different contrast, so that's why we also call it as voltage contrast. So for this type 2 contrast, here the voltage contrast is happening due to the localized specimen charging in the material, uh, and this is happens. Hmm. So here what I was discussing is here, the contrast is happening due to the localized specimen charging, and this may happen in insulating as well as conducting specimen, and this in those specimens they have insulating inclusions, and those inclusions provide different kind of the, the charging effect, and because of that there's contrast happen in the specimen. So here contrast due to localized specimen charging, mainly insulating inclusions. So this non-conducting inclusions, they cause charging effect. So what happens is that the beam injects sufficient energy of electron into the target to develop a surface potential locally that is equal to whatever beam potential is applied. So in this insulating inclusion portion, we can see like varying white and dark spots, and this provides contrast to the specimen. And these are the two type of electric field contrast which we see. Next, in magnetic field case, here also we kind of have two type of contrast. In type 1, case, the contrast arises from interaction of secondary electron with the force field of different magnetic domains which are present in the sample, and this secondary electron is coming when the beam is applied on the sample. Then the secondary electrons come out, and after this secondary electron come out from the sample, they interact with the magnetic domains of the sample itself, and this interaction give different contrast, because if the sample will be having different orientation of domains, then they will interact differently with different domains, the secondary electron, and they will provide contrast accordingly. So here what is happening, like a different orientation of magnetic field, we will have different force fields in terms of, let's say, directionality. So accordingly the secondary electron are deflected in different manner when they come across different orientation of magnetic field, and hence they give a bright and dark bands accordingly, producing an image contrast. So in type 2 case, the magnetic contrast arises when the internal magnetic field interacts with the beam electron directly. So here magnetic contrast arises when internal magnetic field interacts with beam electron. So let's say we have a specimen in certain orientation, and we change the orientation of specimen by tilting it. So for certain orientation of specimen, for one polarity, it may get deflected by the force generated by internal magnetic field towards the surface, giving us more backscattered electron. And when we change the polarity, then uh, it will drag the electron deeper inside the specimen and will reduce the backscatter electron. So this process will again give us a bright and dark band, and so we get a contrast in our specimen. So these are all about a special contrast in scanning electron microscopy. Next we will move on to electron channeling contrast. Just a minute. Sorry for the delay. There's so much noise outside. So next, electron channeling contrast. So these are also called crystallographic contrast. So here, what happens is the regular arrangement of atoms in crystal solid can influence the backscattering of electron because of this regular three-dimensional variation in atomic density in the crystal compared to those with same atoms placed in the near random three-dimensional distribution of an, let's say, different kind of solids. Maybe let's say in amorphous case, as we know, there is no periodic arrangement, so we always find this kind of different distribution of atomic density at different positions, not like crystalline case. So if a parallel electron beam is directed at a crystal array, so if we direct the electron beam into this crystal array, two things can happen. One, like it may get reflected from the surface itself, or it may get inside the crystal. So when this electron beam is directed into this crystal array, so a series of depending on the density of atom, that beam encounter uh, deflection with varying intensity according to the crystal orientation. So when the beam is let's say for certain orientation of this kind of atomic arrangement, there are open gaps between the planes, and So there are certain channels that are present in the crystal, where the atomic packing creates lower charge density, with which the beam electron will interact weakly. So when the beam is aligned with the channel, uh, a small fraction of beam electron penetrate more deeply into the crystal before beginning to scatter. So for beam electron that start scattering deeper in the crystal, the probability that they will return to the surface is reduced, and so the backscattered elect the backscattered electron, the coefficient of backscatter electron, which we denote as eta, that value reduces drastically. So so for let's say other crystal orientation where there are denser atomic packing, the electron scattered at the surface itself, and we have a greater value for this backscatter coefficient. So this to determine this electron channeling, the the different properties of electron beam, like the energy, and which we can relate it to the wavelength as uh, so so by changing the energy, that means we can like by putting certain kind of wavelength, we can uh, check how that beam is behaving with the lattice, and so these properties of electron beam are related to the very important this crystal parameter in and which we uh, give in terms of Bragg's law. So here it defines a special beam incidence angle relative to a particular set of crystal planes with spacing d, at which the channeling condition changes sharply from weak to strong as the beam incidence angle increases relative to that particular set of crystal planes. So for different energy of this electron beam which will fall, different kind of uh, diffraction will happen, and as because of this difference in the uh, atomic density, we are getting different kind of electron coming out, so this gives us a contrast now material. So here difference in contrast we are getting because of different atomic density. So there are different conditions, like how the specimen is prepared and instrument, and depending on the instrument condition, this a contrast varies, and it tells us how we will get a better contrast or not, and This depends on the specimen preparation and instrument condition. But the demerit of this uh, characterization tool is these are not so powerful, as we will see in case of uh, electron backscatter diffraction. So next, moving on to to understand the crystallography of a material, we need to describe the structure property relationship. So by linking the microstructure to the crystallography of a sample, we can get clear picture of the sample, and this EBSD gives us a very nice information about this phase identification and orientation of our sample. So first we'll talk how this electron backscatter diffraction patterns are coming. So this EBSD patterns are originate uh, are obtained in SCM by illuminating a high tilted specimen with a stationary electron beam. So the electron beam which we are putting, they interact with the sample, and they initially they inelastically scattered. And how we can employ these two method? Uh, this can be done in two ways. One by conventional EBSD method, and another one is transmission EBSD method, which we will not discuss here. Uh, so in a given EBSD, in a given EBSD pattern, we see different uh, lines which otherwise known as Kikuchi patterns. So some of the backscattered electron, when this beam falls and there's backscattering, so some of the backscattered electrons, they satisfy the Bragg's condition and are diffracted into cones of intensity with a semi-angle of 90 minus theta. Backscattered electron satisfy uh, Bragg's relation, and they are diffracted into cones of intensity with a angle t minus theta, with this cone axis normal to the diffracting plane. So this EBSD pattern consists of straight bands, which are actually the conic sections, which may have bright or dark centers with respect to the rest of the pattern. So this straight bands are basically Kikuchi lines. So the Kikuchi bands intersect in many locations, and the intersection is called zone axis. uh, Kikuchi band intersection points are called zone axis, and they give us the information about crystallographic direction. Crystallographic direction. So the so this angle between Kikuchi band and the angle between the zone axis are very specific for different crystal structure. So that's why they, for different specimen, they have different crystallographic orientation, and because of that we get different Kikuchi band for different materials. So here it is very important to understand the volume from which the diffraction pattern is coming. um, as we already have seen how much important this volume interaction is in case of contrast. So here in EBSD we don't require, usually don't require high resolution. So the formation of EBSD pattern do depend on scattering and subsequent diffraction of electron. And this Bragg's law, they describe the diffraction of specific wavelength of electron from the plane in a crystal solid. So if there is a large spread in the energy of electron that those are going out of the sample, that we would expect to see those lines in our EBSD pattern due to diffraction. And these lines are almost exactly in the correct position as the Bragg diffraction of electron tells us, based on whatever beam voltage we are providing to produce this pattern. So the whatever the electron is leaving the surface are sort of same energy, those are provided to them. And whatever, if the electron loses more energy, then they are lost to the background intensity. So here we can see for EBSD the tilt angle does play a great role. So when the sample is tilted at a high angle with respect to the electron beam, this tilt helps in obtaining high quality pattern, which we need in this characterization tool. So here we can see the best pattern are obtained at higher tilt angle. Uh, so higher tilt angle, better resolution. So this thing we can see in our next slide here. This shows the backscattered electron energy distribution that is developed from uh, tilted angle of 70 degree and is compared with same distribution from an electron that is normal to the sample surface. So as the EBSD pattern is clearly visible in the previous case, so they must be coming from electron that have lost either no or a small amount of energy. That's why they didn't lose their resolution much. And in the second case here, it is a Monte Carlo simulation of distance from initial uh, beam impact point that the electron emerges from the sample where it is impacting and from where the electron is ejected. So the pattern which is formed from the low loss electron, they provide us better resolution. Pattern formed from low loss electron provide a better resolution. So the high tilt angle limits the spatial resolution attainable due to this elongation of electron beam on the sample surface. So the resolution parallel to the tilt axis is much better than the resolution perpendicular to the tilt axis, and this is due to the high sample tilt angle acquired the EBSD patterns. So here we can write the resolution perpendicular to the tilt angle can be related to parallel one, where here theta is the sample tilt with respect to L perpendicular. So the resolution perpendicular to the tilt axis is greater to if we keep on increasing the tilt axis. So next important point is to know how to index the pattern formed in the EBSD. How EBSD index patterns. So when the pattern is collected, the necessary information for indexing of pattern is derived from the diffraction pattern, and once it is indexed properly, then we can easily get the crystallographic orientation. So for indexing, it is very important to set up the camera properly. So once the camera is set correctly, then the first step, setup of camera for high quality contrast. Then the software extracts the line positions from collected pattern. So in most of the software, it is done through Hopf transform method. Here what it does, it takes straight lines and transform them into points. Take straight lines and transforms them into points, and this eventually are easier for image analysis, which is done by the software itself. So after this, we have to compare the angles between the bands in the pattern uh, with a already existing pattern available in the software itself. Compare the angles between bands patterns with calculated values of interplanar angles from any literature crystal structure. So once a consistent set of indices are found here, the pattern is considered to be indexed here. Then after indexing, how what are the steps involved in EBSD measurement? So first, preparation of sample. It should be free of any damage. Then alignment in SCM. We have to select an optimal uh, tilting of the sample. Then the important parameters involved, selecting proper voltage and current, setting up voltage, current, and respective detector. Then we check for patterns. High quality, we always look for high quality patterns. Then at last doing a mapping of the thing. It is very important here to choose proper pixel size so that our image is not compromised. Then whatever sample we have now, these are all the steps we need to follow for EBSD measurement and whatever sample required we need to analyze it. So EBSD is somewhat unique in analytical techniques in terms of collection of data. So one of the most common way to display EBSD orientation data is with orientation maps. So there are called inverse pole figure map with respect to a specific physical direction. So in order to understand inverse pole figure map, so it is very important to understand the pole figure map and how we interpret this pole and inverse pole figure maps. So this pole figure map are used to answer certain questions such as where does a particular crystallographic direction or plane fall in space relative to some arbitrary physical sample direction or plane, and these pole figures are used uh, for mentioning the proper orientation of the specimen. So we most of the time single pole figure doesn't provide us enough information, so we have to take additional pole figures of different crystallographic directions. So this pole figure is a stereogram with axis defined by external reference frame. So here in this figure we can see it's a series of pole figures from a evaporated gold thin film. Yeah, so in this example it is shown that here pole figures of 111 and 110 direction is shown for 111. There is a large number of poles plotted in center of the pole figure This shows that many of the pixels in the data have 111 direction aligned with the sample normal. So there are additional rings in the 111 pole figure. So these are a result of there being more than one type direction in a cubic crystal, and in a 110 pole figure we can see there is a number of poles in the center of the pole figure, which indicates that there are number of measured pixels with 110 direction parallel to the sample normal direction. You can see. In inverse pole figure, like we say, what pole figures gives us? Pole figures answer question like, where does a particular crystallographic direction or plane fall in space relative to some arbitrary physical sample direction or plane, but this inverse pole figure that tells us what crystallographic poles or planes are preferentially parallel or perpendicular to a specific sample direction. So here we can see this is an example of inverse pole figure for same gold thin film. So here in this figure it is helpful to show all three orthogonal directions so that preferred texture can be visualized. But in here inverse pole figure they shows exactly the same information. Okay. So one should plot this inverse pole figure first so that they will get the idea of an indication of sample texture without plotting pole figures of many different directions. So this we can say a benefit of drawing inverse pole figure. And the z or the surface normal direction of inverse pole figure is the one that carries the most information about the sample. Or surface normal direction of inverse pole figure carries most of the information. Here we can see the high density of pixel orientation, clutter around 111 and less around 110 direction, which seen here in pole figure also. So what are the checklist one should follow after doing this electron back scatter diffraction? So first is what type of specimen we are considering. So this EBSD, they require a properly prepared sample that is very securely attached to a proper substrate, proper support, as it is going to be tilted to high angles to facilitate this EBSD pattern acquisition. So it has to be very sturdily adhered to the support or the stage, and the sample surface should be free of artifacts during the sample preparation stage. So due to high sample tilt uh, and generally most of the time the acquisition time is also very large, uh, one should be careful how one stick it to the surface. So one should be very careful about using uh, whatever tapes one is using, the carbon tapes, or one using mounts like metal graphic mounts. One should be very careful of using those. And as we have already seen, like charging effect in non-conductive samples are very significant. So non-conductive sample may also be lightly coated, not heavily, and it is possible to utilize the variable pressure mode of operation to reduce this charging related artifacts. And next is EBSD detector. So the positioning of the sample and the tilt should be very precisely seen. So once the sample position has been established, this EBSD detector is introduced. So the exact location uh, of this detector are not that important, but the distance between the sample to detector should be very small, so that a large solid angle can be obtained. Small distance between detector and sample, giving us large solid ion. Next, selection of crystallographic phases. So this EBSD, they require possible phases that will be analyzed, uh, which are going to be selected. So EBSD is conducted on samples that are already well characterized with respect to these phases. Next, a microscope operating condition and pattern optimization. Then selection of EBSD acquisition parameters, and then collection of the orientation map. So for here, pattern optimization, one has to do with all the parameters, one has to calibrate for each and every system, and those calibration varies from material to material. And for selection of EBSD acquisition parameter, so successful orientation mapping will depend on this careful selection of different mapping parameters, and among those, a step size uh, and spacing between individual measuring points are very important. A selection of spacing that is too large, missing important microstructural features, and a spacing too small will require longer acquisition time, and those are not going to give us additional information, so it will just take up the instrument time. So one has to optimize these parameters too, and the experimental condition for EBSD acquisition is selected such that it will take the best small map possible to determine if the parameters selected are capable of producing a quality result. So one of the common way to judge a quality is to look at the number or the fraction of pixels in the map that has been successfully indexed to a certain level of confidence. How to judge quality? Look at the number or fraction of pixels in the map that has been successfully indexed to a certain level of confidence. So these are all about EBSD. Next, going to the questions. Voltage contrast is observed in what kind of materials? It is always insulators, because we see kind of charging effect, and because of this charging effect, contrast is produced over our sample. The magnetic contrast arises due to dash upon electron beam as they initially scattered within the specimen. So this magnetic contrast arises due to the internal magnetic field. Uh, we can see in both of the type 1 and type 2, the internal magnetic field either interacts with the secondary electron interacts either with the secondary electrons or the electron beam directly and give us different kind of contrast and features. The electron yield variation due to magnetic deflection result in what kind of images? Because of results in bright and dark bands, because this electron yield variation results in contrast differences, and this contrast differences is coming because of this bright and dark bands. This we can understand, like let's say we have different orientation of magnetic domains, and so when our secondary electron is interacting, or electron beam, either of them, when they interact with one kind of domain, they will either, let's say, one kind of domain will deflect it towards the detector, then another opposite domain will deflect it away from the detector, and this towards and away detector, they will form a bright and uh, dark bands, and they give contrast in this mag magnetic field contrast case. So electron channeling contrast is also known as crystallographic contrast, because they provide crystallographic information of a material. Distance between two lines in Kikuchi pattern implies what angle? Always 2 theta angle. So among the following, which one contributes to electron channeling contrast? In electron channeling contrast, as we have discussed, because of difference in atomic packing density, either the electron will penetrate inside the specimen, or it will get deflected from the surface depending on the atomic packing density. If it is more dense, then it will deflect it from the surface itself. It will not penetrate much. When it is less dense, it will penetrate inside the specimen. Why parabolas appear as straight lines in Kikuchi diffraction pattern is this parabolas appear as straight line because the angle involved are very small. Because of that, this parabola seems to be a straight line. During EBSD scan, the sample is tilted to how much angle and why? So, as I have seen, like if we are tilting the sample more, then we are getting more scattering and also better resolution too. So here 70 degree to get more scattering. When the applied voltage of SCM increases, the interaction volume in the sample they also increases because the applied voltage and interaction volume are directly proportional. So among which of the modes give information about orientation of grains? EBSD. The dark and white patches arises due to compositional difference inside the grains. No, it's not the compositional, it's the orientational difference. So it's false. Dark and white patches arises due to difference in local orientation inside the grain. This is true. Dark and white patches arises due to difference in orientation of magnetic domain inside the grain in case of EBSD. Yeah, true. The contrast we see in the image is a Z contrast. Again in case of EBSD. Z contrast which we usually get because of atomic number differences, but here in EBSD we are getting differences because of the orientation, so not because of atomic number. Also, different atomic density gives us electron channeling contrast. That can also be considered, but again that doesn't give us Z contrast. That is atomic density and this is atomic numbers. So here we don't see contrast because of Z contrast in EBSD. Depending upon the magnetic domain orientation, the secondary electrons deflect either towards or away from ET detector. True. So either they deflect towards or away from the ET detector, and accordingly this dark and bright contrast are formed. The brighter patches have a higher secondary electron yield compared to the darker patches. Higher secondary electrons. True. Because of higher secondary electron, they give us high contrast compared to those having less secondary electrons. That's why a contrast difference is seen because of that. The contrast formation in ECCI depends on backscattered yield. Uh, this statement correct? Yes. In ECCI, we do see backscattered yield because with different atomic density, it this backscattered yield varies. Like with high density, uh, can you see my slides? My slides are visible, right? But not in full screen mode, right? Yeah. Yes, sir. Yeah, because after making full screen, the slide is not changing, right? It's now 18. I've changed my slide. Can you see the change? It's only 18, right? Showing. Oh, now here it is out of full screen mode, right? Okay, now let me present in this way then. Okay, so this one is correct. Then the lower atomic density areas in the specimen gives brighter contrast compared to higher atomic density. No, the higher atomic density will reflect more back electron and it will increase the BSC yield, for which we will get brighter contrast for higher atomic density, not the other way around. So this statement is incorrect. As the beam penetrates more into the surface in the lower atomic density region, the scattering is more effective. No, it is incorrect. The scattering is less effective. This statement is also incorrect. So the correct option will be only statement 1 is correct and other are wrong. So this will be the correct answer, H. Next question. Why specimen stage tilted to 70° in an EBSD scan? This hides the surface roughness such as scratches. No, it is a positive effect. Like if I tilting it to higher angle, then we will get a positive result. So this statement is a negative result. So this is discarded. Produces a flat cosal cone. Yes, it does. Like as we have seen, the Kikuchi lines, those represent each cones. So basically, the flatter the causal cone will be, the better resolution will be getting. So this is correct. To increase the backscattered electron yield, as the EBSD camera is attached at certain part of action, this is also correct. As I have already discussed, like it's very important, like what is the tilting of our sample to get a better resolution. Then electron microscope. The electron beam of wavelength 0.0061 nanometer passes through an electromagnetic lens having strength 0.3 Tesla. Calculate the radius of electron beam. So to calculate the electron beam radius, like the formula is given by R0 equals to 1 by B root over of 2 m V0 by E. Sample current, secondary electron and backscatter electron yield. The primary beam is given by sum of secondary current plus backscattered current plus sample current. So sample current is given as I0 minus secondary electron current plus backscatter electron current. With all values are given, plug it in. Primary electron is 1 micrometer minus 0.3 micrometer minus 0.2 micrometer plus. We can calculate the value of source current, sample current. Then for yield, the backscattered yield is given by eta, which is given as backscattered electron current divided by the primary electron beam current, which is here 0.2 by 1. So backscattered electron yield is 0.2 and secondary electron yield is given by secondary current by primary current, given as 0.3 by 1. For a given wavelength of electron beam and spherical aberration coefficient, proof optimum image aperture is proportional to lambda by Cs to the power 1/4. For this, what we did is, first, as the theoretical resolution, it's given by theoretical resolution given by 0.61 lambda by alpha, and after the disk of confusion by spherical aberration, this is given as R1. Given as Cs alpha cube. So the net resolution is given by 0.61 lambda by alpha plus the Cs alpha cube. So this spherical aberration we need to minimize by using a very small aperture, so we need to minimize the net resolution with respect to the aperture so that we will get minimum spherical aberration. So for that, what we need to do is we need to differentiate this net resolution with aperture, we will minimize it, then we'll get a minimum spherical aberration, and from that we can get the value of optimum aperture value. We'll differentiate it, but we'll get this alpha to the power minus 2 0.61 lambda minus 1 alpha to the power minus 2 plus 3 CS alpha square equals to 0. Then alpha, take it here and equating alpha to the 4 will get as 0.61 lambda by 3 CS and alpha will get proportional to lambda by CS to the power 1 by 4. The optimum image aperture. So here for optimum image aperture, this aperture angle is proportional to lambda by CS to the power 1 by 4. This is what it is asked to prove.